Thank you very much. Do you hear me? Yes. So let me first thank the organizers for this kind invitation, and or the organizers and participants for building up this very exciting and beautiful workshop. Today I will tell you about recent results that I have obtained in collaboration with Antonio Mariti and my PhD student in Milano, Luca Cassia. They concern the classification of two-dimensional superconformal field theories obtained by twist compactification of parent four-dimensional superconformal field theories. Let me spend a couple of words about motivations, why we are interested in such a program, where you know that there is a very general big program of classifying superconformal field theories. And of course, within this big program, looking at two-dimensional superconformal field theory is very important for many reasons, very well-known reasons. First of all, two-dimensional theories enter in the worksheet description of string theory. We know that they have a richer, quite rich algebraic structure that very often leads to the possibility to obtain exact results. And since we are in a ADS3 SCFT2 workshop, we know that two-dimensional superconformal field theories are one of the two main characters of the three-dimensional version of the ADS CFT correspondence. And in particular, it might be that, we hope they can play a role in uncovering properties of three-dimensional quantum gravity. Okay, so which is the general idea that we will follow? We start from a four-dimensional superconformal field theory with a given amount of supersymmetry. I will show you all cases, the procedure applied to all cases n equal to 1, 2, 3, and 4 supersymmetry to begin with. We compactify the theory on two-dimensional Minkowski times a compact Riemann surface with a generic genus G, so this is a generic curved space, compact space. And if you look at the theory on this curved background at low energies, in particular at energies much below the scale fixed by the dimensions of the Riemann surface, we obtain, of course, a two-dimensional theory close or at its infrared fixed point. However, we know that in general, compactifications, generic compactifications, break completely supersymmetry, the original supersymmetry, because the Killing-Spinor equation that you obtain, which is this one, in a very sketchy, written in a very sketchy way, does not have non-trivial solutions once you have a non-trivial spin connection appearing in the covariant derivative. However, as Witten suggested in already 1988, we know that we can perform what we call the topological twist, which means we turn a flux, turn on a flux for a gauge field a U1, in our case, a U1 gauge field for of the theory, and choosing this constant flux to be equal to the gauge connection, of course, the Killing-Spinor equation turns out to have non-trivial and, of course, constant solutions. Sorry? In our cases, we will always have the U1, and I will explain you why. You can have non-abelian groups when you compactify, you have to deal with non-abelian gauge groups when you compactify on bigger spaces. For instance, if you go from 6 dimensions directly to 2 dimensions, compactifying on some 4-dimensional compact space, in that case, your spin connection might require the introduction of non-abelian. No, of course. You have to couple to some U1. Some external background fields, yes, of course. Okay, so what we can do, following this procedure is to classify the resulting two-dimensional theories in terms of the amount of preserving supersymmetry. And once you have done that, you can even infer, as I will describe you, the anomalies, the conformal anomaly of the theory, and classify these theories in terms of their central charge and flavor anomalies, written in terms of the anomalies, the global anomalies of the original parent four-dimensional theory. Well, we do prefer to start with the superconformal, as I will tell you, or the superconformal theory is not necessary. In fact, people in general, yeah, but since we want to preserve, hopefully, superconformal invariance in two dimensions, the most natural thing to do is to, to try to keep as much as possible your supersymmetry. Okay, so the plan of the talk is the following. I will describe how we can apply directly this procedure to different cases, focusing primarily on the n equal to 3 and n equal to 4 cases. And at the end of the talk, I will show you how to compute the central charge in terms of the four-dimensional data, and I will conclude with some comments and perspectives. Okay, there has been already quite a lot of work done in literature concerning the compactification of four-dimensional supersymmetric theories on compact Riemann surfaces. They do concern, in particular, compactifications of the original four-dimensional n equal to 2, primarily n equal to 2, with the idea to perform localization, of course, but some work has been done also for n equal to 4 and n equal to 1. What we are going to do today is to, redo the whole procedure within a systematic framework, which is nothing but the superconformal, the superconformal gravity framework. And using this systematic approach, we will, of course, reproduce the known results present in literature. We will find new ones, and in particular, we will be able to apply this procedure now to n equal to 3 four-dimensional theories that has not been considered earlier, of course. Okay, so just answering your question, I think the most natural way to define a four-dimensional superconformal field theory in four dimension on a curved space, which is, remember, Minkowski, two-dimensional Minkowski times a compact Riemann surface, is to follow certain, say, basically Festuccia-Seiberg idea to couple the original four-dimensional theory to conformal supergravity, and then freeze the gravitational modes, the bosonic gravitational modes, to describe the desired geometry, possibly turning on some additional gauge fluxes, and of course setting all fermions equal to 0. Setting fermions equal to 0 will define your surviving Killing spinors, in fact. Why this is a natural way to proceed? Because, of course, by definition, conformal supergravity preserves superconformal invariance. So this is a way to put your superconformal theory on a curved ground in a safe way. Killing spinor equations that arise setting the variation of fermions equal to 0 contain already gauge fields, terms in the covariant derivative, contain gauge fields associated to the R-symmetry group. If the R-symmetry group contains U1 factors, you are basically ready for performing topological twist. And what helps us now is that Weyl multiplet and the complete content of the Weyl multiplet and its nonlinear supersymmetry transformations at this point is well known for all the cases 1, 2, 3, and 4. So we have all the tools we need to proceed. Okay. So I will describe in quite detail the simplest case, n equal to 1, but as I said, the most interesting things happen for extended cases. So to begin with, we start with the four-dimensional n equal 1 superconformal field theory coupled to the n equal to 1 Weyl multiplet that, of course, contains fields that describe the geometry, and what we are interested in contains the gauge field associated to the U1 R-symmetry of the theory. We will choose the following geometry. We will consider a compact Riemann surface of generic genus G with the constant curvature, and the curvature is chosen to be proportional to the volume to form of the Riemann surface, proportional by with this constant K, which is basically the quantization of gives the quantization condition of this curvature, and K is basically proportional to 1 minus G. So just to follow what I will tell you later, just keep in mind that when we are working on the torus flat case, K is equal to 0, otherwise K is different from 0. So we will distinguish these two different cases. Sorry. Nu, of course. Good question. Nu is the volume of the Riemann surface, of course. You can infer it from here. The integral of omega 2, 3 divided by 2 pi is nu. Okay. If we set, of course, the variation of your fermionic gravitino equal to 0, you get, and the variation in this case contains both variation due to supersymmetry transformations and superconformal transformations with parameter eta, you will end up with this equation. And when you have to you want to preserve some supersymmetry, you have to set this equation equal to 0. We look for solutions corresponding to eta equal to 0 and d mu epsilon equal to 0. So we require the two terms vanishing separately with the, well, I don't want to enter into details here, but they are actually not really independent. So d mu epsilon equal to 0 in fact implies eta equal to 0. Okay, you can work a little bit on your killing spinor equation. If you apply an extra derivative, you can trade your original equation with algebraic equation, where, of course, I keep the U1 gauge connection turned on. This is the one that I need to perform topological twist, and this gives rise this term proportional to the curvature, the gauge field strength. Okay, now if we choose the field strength of the gauge R-symmetry connection still proportional to the volume to form on sigma with a suitable condition, quantization condition, the killing equation becomes an algebraic equation that you can easily solve. How? Well, first of all, we can write the four-dimensional spinor in terms of its Weyl components, and if we can, for instance, I will just focus on the positive chirality component. If you look at the destiny of this Weyl component under breaking of the four-dimensional Lorentz group into the two-dimensional Minkowski times the spin 2 group on sigma, this epsilon will just break into one epsilon plus and epsilon minus that have charges 1, 1 and minus 1 respectively for these two groups. Okay, this is not the end of the story, because we know that n equal to 1 theories can have extra global symmetries, and if we have extra U1 global symmetries into the game, they can be either flavor or baryonic symmetries. We can even play with them, and in fact we can think of turning on a flux for the gauge connection associated to this U1 global symmetry. This, if I want to do it in a supersymmetric way, this implies turning on the whole n equal 1 gauge multiplet and imposing that the gaugino variation, gaugino has to be 0, of course, when I perform a compactification. If I impose the variation of the gaugino under supersymmetric transformation to be 0, I get an extra condition that can be solved non-trivially by choosing a particular constant non-zero flux for this extra gauge connection on your Riemann surface, and a non-trivial value for your auxiliary scalar y. And the condition that we get as an extra condition on our Killing spinors is nothing but a chirality condition in 2 dimensions. Okay, so in general, in the most general case, we have to solve a couple of equations. The original one coming from the variation of Gravitino, and the second one coming if we turn on fluxes for extra global symmetries. We can solve these equations and classify the equations in terms of surviving supersymmetries, and this ends up to be summarized in these 2 tables. So the first table is for k different from 0, so when we compactify indeed over a curved background. And according to the particular choice of your original R-symmetry flux, remember it was proportional to this parameter A, we can end up with 2,0 or 0,2 supersymmetry in 2 dimensions. Of course, if k is equal to 0, you can have the most supersymmetric case, because if k is equal to 0 there, it is not necessary to turn a flux on, so we can set A equal to 0. And of course, if you do not turn on any other global U1, you will end up with the whole amount of supersymmetry. Otherwise, the chirality condition will select 0,2 or 2,0. In this procedure, it is quite interesting to see what is the destiny of the U1s of your theory. What I want to do is to count how many U1s I had in the parent here in theory in 4 dimensions, and see, and supposing that they survive in 2 dimensions, so that nothing gets broken, see how they can, and they have to indeed reorganize in order to give the right R-symmetry in 2 dimensions plus probably something else. And in fact, this is the counting, well, in this case it's very simple. In 4 dimensions, we start with the U1, the R-symmetry U1, plus an extra U1, which is nothing but the Lorentz generator on sigma, which assigns charges plus and minus 1 to our 2-dimensional spinors. Therefore, if we float, for instance, to the 2-0 theory, it's easy to see that in this case we are left with a U1 R-symmetry generated by this particular linear combination, and we are left with the second, we start with 2 U1s, we have to find 2 U1s. The second U1s we find is indeed the flavor U1 for the 2-dimensional theory. Instead, if you flow to 2,2, the maximal supersymmetric case, in this case you need U1 cross U1, and in fact the 2 combinations build up the U1 R-symmetry generators. Okay, these tables basically reproduce the results that have been found already in literature. The same thing now can be applied to the n equal to 2 case. I will go quite fast on the n equal to 2 case. What happens if we increase supersymmetry? If we increase supersymmetry, what happens is that when you couple your 4-dimensional theory to the n equal to 1, n equal to 2 in this case, superconformal gravity, your Weyl multiplet will contain more fields. In particular, it will contain, as usual, the fields describing your geometry that we choose the same as before, and the gauge fields associated to the R-symmetry group, that in this case is of course U1 cross SU2, plus a number of fermionic fields. In this case, beyond the Gravitino, we also have auxiliary fermionic fields. Therefore, we have to set all fermions equal to 0. So what happens is that in this case, you get more than 1 Killing spinor equation. On the other hand, you have more fluxes to deal with, so balancing the two, the doubling of the number of equations, but the fact that you have more fluxes leads you to have still non-trivial solutions. In fact, we can see that non-trivial solutions exist if we turn on a flux, a constant non-vanishing flux for the gauge field associated to U1 of your symmetry, and another flux for the gauge field associated with the Cartan of SU2. Okay. Plus, this case, I have to turn on also a non-zero value, constant non-zero value for the auxiliary scalar d in order to ensure that this equation is satisfied. Still, we can add flavors as we did before, and this requires adding the whole n equal to 2 gauge multiplet associated to this U1 global symmetry, imposing that the variation of the gauge genus is equal to 0, once again with a suitable choice of your background fields in the Weyl multiplet, you get sort of chirality conditions in 2 dimensions. And what we end up with, of course, splitting 4-dimensional spinors in terms of 2-dimensional ones, is this table of solutions that once again reproduce known results that we found already in literature. And now we come to the new case. This is completely new because the existence of n equal to 3 superconformal theories in 4 dimensions with no enhancement to n equal to 4 is a quite recent discovery. This has been discussed in these papers by Aroni Eftikiev, Garcia Estevarria Regalado, Aroni Tachikawa. And, well, these theories have quite nice properties that we can summarize in these few points. First of all, these theories exist only at strong coupling. There is no Lagrangian description because once you require to have a Lagrangian description, immediately you jump to n equal to 4. So for the same reason, they correspond to isolated fixed points. There are no exactly marginal deformations. Otherwise, you jump to n equal to 4. Conformal anomalies have been analyzed in this paper by looking at these n equal to 3 theories as from the point of view of being n equal to 2 theories. And what they found is that the conformal anomalies satisfy the same condition as the n equal to 4, A is equal to C. As in the n equal to 4 case, they cannot have flavors, extra flavor symmetries. Their symmetry is SU3 cross U1, and the only free multiplet that we can build up in this theory is the vector multiplet, which is the same, with the same content of the n equal to 4 vector multiplet. Okay, if we want to apply our general procedure to this case, of course, we have to couple this n equal to 3 theory to n equal to 3 conformal supergravity, which has been known since 1981, but only very recently, thanks to this paper by Van Pruyen and his students, Van Moyden. At this point, we know the complete content of the Weyl multiplet and the corresponding nonlinear superconformal transformations. No, this is well, in n equal to 4 case you do have,
yeah,
but even in this case.
So, well, so I don't understand. Is this an off-shell multiplet? Does it close off-shell, or do you need to impose some equations of motion?
No, I think it is off-shell, if I remember correctly. I mean, what they do is really to find, they really manage to find the complete set of algebraic transformations. So this is the complete. I just listed the independent fields. I do not include here the composite fields that you usually have, but except for that, this is complete. Okay, so once again, you have the appearance of the fields described in your geometry and the gauge fields associated to this U1 across SU3, our symmetry group. We set fermions equal to 0. This time fermions are the gravitinos and extra fermionic degrees of freedom, auxiliary degrees of freedom. Therefore, we have even more conditions to impose, 3 this time. But we can play with quite a number of fluxes because this time we have as an R symmetry U1 cross SU3. So we can turn on a flux for a constant flux for U1 for the one gauge field and for the gauge field associated to the Cartan generators of SU3. And once again, you can play with non-trivial auxiliary scalars in order to make the second and the third equations equal to 0 identically, and you are left with the first one, which will give you non-trivial solutions for killing spinors. Okay, so this is the classification of solutions. Depending whether you are working in the torus case or for more generic curved Riemann surfaces, you have, of course, a different amount of surviving supersymmetry. Well, this is the asymmetry which we have to survive in 2 dimensions. Whether or not this two-dimensional let's say supersymmetric theories exist, we cannot tell anything yet. I mean, this is something that this is just a classification of the most general set of solutions, but of course one has to use different approaches at this point in order to construct explicitly some of these cases. This one, the first one? Yeah, no, well, I don't know what to tell you except that this is what comes out by solving, I mean, classifying the number of, kind of Killing spinors that you have as non-trivial solutions. This is what comes out. This is the complete features. Well, we can go through the calculation to see what. Okay, so I read this in I write this in red because I want just to take this as an example to show you how the U1 counting works in this case. Well, things are well functioning as before because we start in 4 dimensions, this case with 4 U1s. We have the U1 asymmetry generator, the 2 Cartan of SU3, plus, remember, the extra U1 coming from compactification. And out of these 4 original U1s, we have to build up 4, hopefully 4 U1s in 2 dimensions. How do they arrange? Well, let's consider this specific case. In this case, the killing spinors surviving are these ones. So we have 2, 4, in fact. And we can easily conclude that we will have a surviving SU2 from the original one acting on the right sector. And this is lambda 3 as a Cartan, the reduction of lambda 3 to SU2 as a Cartan, while the I have other 2 combinations out of TR and M23 which generate the asymmetry U1 left, U1 right. We are missing 1, no, because in fact from the killing spinor equation you can see that we are left also with a flavor U1 symmetry given by this generator, so the counting of U1s works. Okay, finally we can do it. We can do the same thing for n equal to 4. In this case, we couple the theory to n equal to 4 Weyl multiplet. In this case, which coupling? Yes. Yes. So are you asking with? Yes, of course. I mean, this is sort of infrared flow, I would say. It's a dimensional flow, but well, it might be. I mean, we don't know. As long as we do not have an explicit example, we cannot say. But okay, now, as I said, we can go through the same procedure for n equal to 4. Let me just stress that in this case, the R symmetry group is SU4. We do not have a U1, an extra U1 anymore, and this makes the difference. So we can still play the same game, turning on constant flow.
Right? The n equals 4 superalgebra doesn't close off shell to my knowledge, or does it? I mean,
I thought it does.
So
Normally it's off shell.
it's off shell.
Yeah.
Vector,
Yeah.
then it's not. Vector map is not off shell. You miss it.
Yeah, that's true. Yeah.
And you only need this one.
Yeah. Okay. So we can, as I said, we can turn on fluxes along the Cartan directions of SU4. So we still have 3 fluxes, as in the n equal to 3 case. And solving the equations, this is what we find. N equal to 4 was covered already by different author in the past, but what we do find right now is an extra solution, this 0,6, that potentially is there because there is a solution, a trivial solution corresponding to this amount of surviving supersymmetry. This is, I mean, a new solution, but as I said already before, as long as we are not able to use different tools to prove that indeed such kind of solution, such kind of theory can actually exist, this is just, wishful thinking. One possibility might be to try constructing some, or just to investigate whether on the dual gravity side there is the possibility to construct backgrounds that might potentially lead to some such a very chiral 0,6 solution in conformal field theory. Okay, in the the counting of U1s and the reconstruction of the R symmetry group works as before, but now it happens something that we don't know actually how to deal with, still because we don't know any explicit examples yet. What happens in this case, the 4-4 case, is the following. If I do the usual U1 counting, I do find well, n equal to 4,4 is generated by these two Keeling spinor solutions. I do find, in fact, SU2 left cross SU2 right surviving as an R symmetry, which is fine, plus a flavor symmetry, which comes from the Keeling spinor. So starting from the original 4 U1s, I do have already 1, 2, 3 U1s. What is the 4th one? In this case, what happens is that the 4th one is generated by this linear combination, and it is sort of a U1 non-chiral, acting on both chirality sectors of the two-dimensional supercharges. In this way, it assigns plus, let's say, charge plus to the left sector and minus charge to the right sector. What is this symmetry? We don't know. Many things may happen. It might happen that when we flow to 2 dimensions, indeed we lose this symmetry because it gets broken. It may happen that this symmetry flows to 2 dimensions as an outer orthomorphism of the algebra. It may be that this symmetry has to do with the bonus symmetry in 2 dimensions, or may combine with the bonus symmetry to give a chiral U1. This is something that, you know, is still an open question, but looks quite interesting to investigate. Okay, in the last 5 minutes, I will tell you how we can infer the anomaly, the conformal anomaly, in particular the central charge of the 2-dimensional theory from the 4-dimensional anomaly coefficients. So we focus, but this can be done in any case, but just to be definite, we focus on the reduction of an n equal to 1 superconformal field theory to 0,2 superconformal field theory. Following and generalizing what these people did in this beautiful paper, Benini, Bobev, Crichigno, we provide a general formula for the central charge of the 2-dimensional theory written in terms of the four-dimensional, as I said, four-dimensional data, which means global anomalies, global anomaly coefficients in 4 dimensions, and the geometric structure of the Riemann surface we are compactifying on. We basically need two ingredients, two basic ingredients. The first one is the following, is what was introduced by Benini-Bovev, called the C extremization. What happens is that in 2 dimensions, we know that the central charge, the right central charge, is proportional to the symmetry anomaly coefficients entering this OPE. When we flow from 4 dimensions to 2 dimensions, remember that we start with n equal to 1, so we start with a U1, or symmetry U1 in 4 dimensions. You may easily accept that when we flow to 2 dimensions, the symmetry generator of the U1 in 2 dimensions will be, in general, a linear combination of the 2-dimensional reduction of the original U1 generator plus possible other U1 generators associated to global symmetries that you have in your theory. Of course, if you do not have extra global symmetries, the story ends here. But suppose that we have extra global symmetries. This is what you have to assume from the very beginning. You have to be very democratic, so every U1 may enter the construction of the symmetry in 2 dimensions. And of course, if you assume that there might be this non-trivial combination, you end up computing what they call a trial central charge, which is of course function of these arbitrary coefficients, psi. How do you determine this psi? So how you determine the exact generator of the U1 symmetry in 2 dimensions? By applying C extremization. So they prove that these psi are determined by the condition that the derivative of the C trial respect to these parameters has to be 0. This is the first ingredient that we need. Of course, the second ingredient that we need is to find out the explicit expression of this KRR for our 2-dimensional theory, which comes from 4 dimensions. This can be obtained from the anomaly polynomial in 2 dimensions that we assume to be identified with the anomaly polynomial in 4 dimensions once you integrate over the volume of your Riemann surface. If you apply this procedure, you end up with your KRR, so your anomaly coefficient, which is given by this trace of TR, TR, T, where TR is in fact the trial symmetry that we are considering, the linear combination with this arbitrary parameter xi, and T is indeed the generator, the twisting generator, so the generator that we used to perform a topological twist. So it will be a function, of course, of this non-vanishing constant fluxes that we have turned on. Okay, so we have this trial KRR, therefore this trial central charge, which depends this time on 2 sets of parameters. If we apply extremization, we end up with the general formula for the central charge, which is given by this expression, where you find, of course, a dependence on the geometry of your Riemann surface through the volume and the curvature K. It depends on the way you perform your topological twist. It depends on the value of the fluxes that you have turned on in 4 dimensions. And it depends on the 4-dimensional anomaly coefficients defined as usual. This is the trace on Weyl fermions. Okay, what is nice is that if we now use the Toft anomaly matching condition, we can compute these anomaly coefficients in 4 dimensions in the ultraviolet. Well, hopefully the 4-dimensional theory has a weak coupling description, a Lagrangian description, and from this information you build up the central charge of your infrared 2-dimensional theory. This formula has been already checked in many cases, in particular in these papers. They looked at n equal to 4, reduction of n equal to 4 super Young-Mills, and reduction of n equal to 1 quiver gauge theories. And what they found, and what has been also discussed in this paper from a dual gravity point of view, is that it's a nice picture. Even if in your original four-dimensional theory you have baryonic flavor U1s that do not mix with the asymmetry of your four-dimensional theory, when you flow to 2 dimensions, these baryonic symmetries will in general mix with the asymmetry, the original asymmetry, to build up the exact asymmetry. Okay, so let me just conclude. So what we have done, it was just to make a systematic investigation of all possible configuration of 2-dimensional superconformal field theories reduced from dimensions. This is just the beginning. I mean, even in literature, there are already many developments, but just partial developments, so there is still a lot to be understood. First of all, it would be nice to construct explicit cases, in particular if we were able to discuss some n equal to 1, 2, or 4 cases, and really see how the theory flows to 2 dimensions, and whether we are really able to construct the 2-dimensional theory from the point of view of the matter and the field content. This is certainly important. As I said already, we should find argument, maybe dual gravity argument, or engineering membrane constructions to prove, to support the existence of these solutions, these theories that we find, or to discharge them. It is certainly very interesting to see what happens to 4-dimensional dualities when you flow to 2 dimensions. This is already being discussed, partially discussed in these papers. There is still room for many developments in this direction. This is something that I would really like to understand, how to flow from even and odd dimensions, so in particular how to flow from 4 to 2 going through 3 dimensions, or generalize this construction that we have done to more general compactifications, like for instance the ones that will allow us to go directly from 6 to 2 dimensions. Other possible developments could be to see how 4-dimensional, deformations of supersymmetric theories in 4 dimensions may affect or how they get translated in 2 dimensions. But this is still to be done. Thank you very much.
One question is, the n=3 theory could be obtained by modding out the n=4 by a symmetry that is a mix of R, like that's as we did like in 98.
Yes, I know,
right?
I know. In fact, we were using your paper, I know.
So if you start with n=4 and do that, and you look at the dimensional reduction, you're sure to find the models that you have already found with the n=3, or is there any surprise there?
No, I would not be surprised. No, I would expect, we'd be surprised not to find any.
So if you want, maybe the interesting question is slightly different. Is there an n=3 that cannot be obtained in that way? I mean, can one say?
Well, in principle, yes, because, well, it's true that when they build up n=3 Weyl multiplet, for instance, they do it from n=4. Yes, no, you can even do that. Yes, you have to break n=4 in a very hard way in order to be sure that whatever you do then in n=3, you do not risk to enhance to n=4, yes. But I think, yes, but this is something that we are discussing, but I think I would be quite optimistic that one can find something.
So I don't see other questions. There were already. Thank you very much again.
Thank you.